Have you ever stopped to think about how your laptop, your phone, and your smart TV can all use the same Wi-Fi network at the same time without turning into a jumbled mess of digital noise? Well, today we're going to pull back the curtain and meet the invisible traffic cop that makes it all possible, the data link layer.
I want you to imagine a world with no traffic rules. On the digital highway, this is exactly what it would look like. Every single device just trying to shout its data out at the exact same time. And the result? You guessed it, constant collisions, garbled data, and a network that's pretty much useless. It would be pure digital chaos.
So here's the big question, right? How does your network, right now in your home or office, avoid this absolute nightmare scenario? How does it figure out whose turn it is to talk and make sure your data gets through cleanly millions and millions of times a day?
Well, the answer lies in a very specific set of rules, kind of like a hero working behind the scenes. We're talking about layer 2 of the network model, the data link layer, and its entire job is to bring a sense of order to all of this potential chaos.
The best way to think of the data link layer is as the ultimate translator and, a logistics manager. Its main gig is to take the data that your software understands, all the stuff from the layers above it, and get it ready for its big journey across the actual physical hardware, like your Ethernet cable or your Wi-Fi signal.
So how in the world does it do that? Well, its first core job is all about packaging. It's a lot like a postal worker who takes a letter and puts it inside a very specific kind of envelope, complete with a to and from address. The data link layer does pretty much the same thing, but for your data.
And this slide, it shows the process perfectly. That chunk of data from the layer above, which is called a packet, gets neatly wrapped up inside something we call a frame. This frame is that special digital envelope. It adds a header at the front and a trailer at the back, and that contains all the info needed for just the very next step of its local journey.
So let's peek inside this envelope, shall we? The very first part of that header is the start frame. It's basically a digital flag that yells out, "Hey, listen up, a new message is starting right now." This is what tells all the other devices on the local network to start paying attention.
Okay, next up, and this is absolutely crucial, is the address field. Now, this is not the final cross-country destination for your data. No. Think of it more like the specific house number on your street. It's the address for the very next device in the chain, whether that's your home router or the next switch down the line. It's all about that local delivery.
And then, at the very end, tucked away in the trailer, we find the frame check sequence, or FCS. What's so cool about this is that it's basically a digital spell check. The device that sends the frame does a quick little math problem on the data and sticks the answer right here. When the frame arrives, the receiving device does the exact same calculation. If the numbers match, perfect, the data's good. If they don't, it means the data got messed up along the way, and that frame just gets thrown.
Okay, so we've packaged our data perfectly inside this frame. But wait a minute, that still doesn't solve our original problem of everyone trying to talk at once. And this brings us to the data link layer's second, and maybe its most important job, deciding who gets to use the network and when.
This whole set of rules has a name, Media Access Control, or MAC. You can just think of it as the traffic light system for that digital intersection. Its entire purpose in life is to manage who gets access to the physical network, the media, to make sure those crazy collisions we saw earlier just don't happen.
So, what do these digital traffic rules actually look like? Well, it turns out there are really two main strategies for controlling the flow of the conversation. The two main ways to do it are kind of like a free-for-all system and a more polite take-a-turn system. And as you can imagine, each one has its own strengths and is used in different kinds of situations.
First up is the free-for-all, which is officially called contention-based access. In this world, devices basically say, you know what, I'll just try to send when I'm ready. It's really fast when traffic is light, but since anyone can try to talk at any time, collisions can and definitely do happen. This is the system that your Wi-Fi and your standard Ethernet networks use, mainly because it's super flexible and makes it easy for new devices to just jump into the conversation without needing permission.
The second method is called controlled access, which is that take-a-turn system. Here, the devices are a lot more polite. They basically say, hey, I have something to send, but it's not my turn, so I'm just going to wait. Only one device is allowed to transmit at a time, which, as you can guess, completely eliminates collisions. It's way more orderly, but it can be a bit slower if a device gets its turn but has nothing to send.
And this table really sums it up nicely. Contention-based. The free-for-all is great for our everyday use where a little bit of overhead is totally fine.
But controlled access, that's better for networks where you absolutely positively cannot have collisions, like in some industrial or really time-sensitive applications.
So how does a network even decide which method to use? Well, a lot of the time, that choice is dictated by the network's logical map, what we call its topology. And in simple terms, topology is really just the way all the devices are laid out and connected to each other.
Take a look at this. This is a multi-access topology, a bit like an old-school Ethernet bus. See how all the computers are connected to the same single line? This is just like a party line on an old telephone. When one person talks, everyone else on the line can hear them.
So, if everyone is on that same line, how on earth do you keep them from all talking over each other? You have to use a very specific set of rules.
You use the listen before you talk rule. This is contention-based access in action. A computer literally checks the line to see if anyone else is transmitting. If it hears silence, great. It goes ahead and sends its frame. But if it detects someone else is already talking, it just waits. It's simple, it's elegant, and it's the foundation of how Ethernet has worked for decades.
But here's a detail that is just fascinating. That frame, that digital envelope we talked about, it's only good for one specific part of the journey. As your data travels from your computer, maybe through a router, across a satellite link, and then over to a Wi-Fi network, it gets unwrapped and rewrapped in a brand new frame at each and every hop. Why? Because the rules for an Ethernet frame are totally different from the rules for a satellite frame, so it has to be repackaged for each type of media it crosses.
So let's bring it all home. The data link layer really is the ultimate translator. It's that critical, essential link that connects the abstract world of your applications and your software with the real physical world of cables, radio waves, and all that hardware. Honestly, without it, the internet would just be that chaotic mess of collisions. It's the invisible traffic cop, working tirelessly to make sure billions of digital conversations happen smoothly, packaging every piece of data and managing the flow, one polite, local hop at a time. So, the next time you connect to Wi-Fi, maybe you'll think about it for a second. All those silent rules that are turning potential chaos into a perfect connection. It's this incredible unseen ballet of framing and media access, happening every single second, just to get your data where it needs to go.